A harmonic oscillator is something which, when moved from its original position, a restoring force acts on it to bring it back to its original position. The momentum shoots it beyond the original position on the reverse side, and the restoring force now changes direction. This phenomena continues and the harmonic oscillator begins to vibrate in SHM about its original mean position with a frequency which is characteristic feature of that particular thing and is called its natural frequency. In this video, I'll show to calculate the natural frequency of some simple harmonic oscillators. Before that, it will be worthy to note that the angular velocity omega is equal to 2 pi divided by t, where t is the time period of oscillation. Therefore, omega equal to 2 pi n, where n is the frequency of oscillation. Number 1. An oscillating simple pendulum. When a simple pendulum is moved from its original position, the restoring force acts due to the weight mg of the bob. At this position, it is resolved into two components. This component balances the tension T in the string. This component is responsible for the restoring force. When theta is small, sine theta is equal to theta and displacement AB equal to x, which is equal to L into theta. So the restoring force is clearly proportional to the displacement x, and so the oscillation is simple harmonic. Comparing the differential equation of SHM, we get omega square equal to g divided by L. But omega equal to 2 pi n. Eliminating omega, we get the natural frequency of simple pendulum. Number 2. Oscillations of mass-loaded spring. Let the length of the spring be capital L. When we load the mass, it elongates further by a length small l. This small l is obviously proportional to the weight mg of the mass. Here, k is the spring constant. If we move the mass further below by a distance x, then the restoring force will be this. We see that the restoring force is proportional to displacement x, and so the oscillation is simple harmonic. And this is the natural frequency. Oscillation of a liquid column in U-tube. The liquid column in this limb is raised by creating vacuum. This level tends to come down due to the extra weight of this liquid level. Here also restoring force is found to be proportional to displacement x, and so the oscillation will be simple harmonic in nature. The natural frequency will be this. Number 4. Oscillation of a floating cylinder. When the cylinder is pressed down by a distance x, the restoring force will be due to the upthrust because of the additional immersion. Here restoring force is proportional to the displacement and the oscillation is simple harmonic. The natural frequency is this. Number 5. Oscillation of a confined gas in a cylinder pressed by a smooth piston. The piston is pressed by a distance x. The pressure of the gas increases and the increased pressure acts as restoring force on the piston. To calculate the increased pressure, we have to consider the process as adiabatic, where PV to the power gamma equal to constant because the change is very rapid. Here also restoring force is proportional to displacement x, and so the oscillation is simple harmonic. The natural frequency is this. Now, summarizing the calculated natural frequencies of different harmonic oscillators, it can be said that the natural frequency of any harmonic oscillator depends solely on its geometry.